My name's Fred Vocasek. I am the senior lab agronomist, and senior is supposed to imply some, maturity or wisdom or whatever, but it just means I'm the oldest one in the crowd. So, what I wanted to do today was cover a few things about soil testing, some questions that we've gotten over and over and over again, and a couple things on soil testing, some of the things we're seeing, and also I was going to talk about the topic of soil carbon. Seem to get a lot of questions about that. So with that, one of the things is we're dealing with is the weather events. Severe weather events affect the soil results. I worked at ServiTech now 39 years. So gone through a couple of severe droughts, couple of situations where we had extreme rains and different areas. And our laboratories, our headquarters is in Dodge City, but we've got a laboratory in Amarillo, Texas, and one up in Hastings, Nebraska. So we cover this high plains. So we see a lot of changes, a lot of extremes. But when we get situations like this, like we've had the last year or so, things don't work quite like we expect them to work. And so we get some head scratching. And Mother Nature throws us some curves every so often. One of the things that we do see, and we've seen traditionally, is when we have a drought period cycle, we see our soil pHs drop. And they may drop as much as, I've seen them drop as much as half a point, sometimes even more than that. And this is just a natural occurrence. This is Frank Sikora, who is from University of Kentucky, and this was he mapped out here, and this is a good example. They had a severe drought in Kentucky, and so he went county by county and used the Palmer Drought Index and mapped out and compared the soil pH to the Palmer to the Drought Index. And so we see here when it's dry, we're at 6.5, but we've dropped almost a full half point in this situation, and we see this very, very commonly. I guess the advice would be not to panic. This is a couple of natural changes in the soil. The pH shows up. Typically, we get a rebound if we get back to normal rainfall, whatever you define as normal. After a career, I'm not sure there is such a thing as a normal year. Every year, there was a farmer about my age when I was starting my career. His name was Ivan Klopper. And Ivan gave me a piece of wisdom that I've never forgotten. He said, Fred, you have to remember, you don't get 20 years experience farming. You get 1 year's experience 20 different times. And that's probably the most profound statement I've heard. And it's true. So we see these things change, but we typically see these things drop down and hopefully they'll drop back up. But one of the things we are seeing as a long-term trend is we are seeing soils get more and more acidic across the plains. Dave Green is one of our territory managers. He's in the process of retiring, but lives in Haxton, Colorado. And a few years ago, he put together some of his. He'd been out there 30 some odd years, but 35 years, and he put together a bunch of his soil test histories on these couple of fields, a few fields, and looked at what happened. So he looked at the soil pH in the neighboring pastures. Now these are fields. This is dry. These are dryland fields, predominantly corn and wheat or some kind of rotation. 15 to 18 inches rainfall zone. But we see over time, over a period of 10, 20, 30 years, we see that soil pH drop slowly and slowly and slowly until eventually we come from 6.5 where things are good. We get down here, once we drop past 5.5 and 5, especially with wheat, we start seeing some problems show up. And, we've seen some soil pHs out there, dryland fields. People think of Colorado as, land of high pHs, but it's not. I've seen some pHs out there, 4.5. On occasion, even I've seen a 3.7, 3.8 sandy soils. But this is kind of a long-term trend. So the thing about it is when I calculate it, it's dropping 4/100ths of a unit of pH a year. Okay, so that's not something that you pick up very, very quickly, but over a period of years and slowly and gradually that soil pH is dropping. And we're seeing this across the board. And this is kind of my rule of thumb. when we use most nitrogen for anhydrous ammonia, urea, UAN solution, the conversion of the ammonium fraction to the nitrate fraction generates acidity. And just a rough rule of thumb I use, it takes about 2 to 3 pounds of ag lime to offset the acidity for a pound of nitrogen we apply. And so what's happened here in Dave's situation over the years, that 40, 50, 60, whatever pounds in the wheat slowly and surely drop the soil pH. And like I said, we're seeing this come across the board. So you may see in this year's soil samples, you may see the soil pH drop. And like I said, hopefully it'll, it might rebound, but it may be on that downward decline. And this was especially noticeable here because in 2012 was when the drought hit that Northeast Colorado area. And he said they started to see problems, not only the soil pH problems from aluminum toxicity, damaged the root system. In that drought situation, here the root systems, we thought they're probably able to recover, even though we had a pH problem. But the root systems recovered, but it was so dry that spring, those root systems never recovered, and so it became very, very prominent. So that's something we need to keep in mind. Another thing that we see sort of as a trend is we've reduced the amount of tillage. We don't, obviously, most areas at least don't plow and do as much tillage, but we can run into a situation of nutrient stratification. And this happens to be a field that one of our customers sampled. This is a strip till field. It was over by Plains. And he pulled a 12-inch sample. And if you look at the average of the 12-inch sample, our pH was 5.9 and our phosphorus was 32, which would not seem to present any problems. But what he did was he broke it up into 3-inch increments. And if we look at the top 3 inches, we had a pH of 5.1. Once we get below, keep in mind that each unit of pH, each change in 1 unit of pH is a 10-fold change in the acidity. So as we go from, let's say pH 6.7, pH 5.7, that's a 10-fold change. With pH 5.7 to 4.7, that unit change, it's 10 times 10. It's a 100-fold change in acidity. So once we drop, pH 7 is neutral. Once we start dropping, once we hit that 5.5 on down, it drops very rapidly because the acidity increases quickly. So we've got, essentially, we've developed an acid surface soil, and our pH in the subsoil is probably what we would typically expect. But we've also, because phosphorus doesn't move very readily in the soil, we have developed a stratification, a layering of that phosphorus. So what, if we look at corn or wheat or whatever, if we're planting in that top inch, inch and a half, 2 inches, whatever it is, we are planting in an area, we've got plenty of phosphorus. 77 is a high phosphorus test. But at this pH, we start to see some damage. So we can actually have a phosphorus deficiency. Now, that's not a soil deficiency. We have plenty of phosphorus in the soil, but it could be a plant deficiency. The example I give would be, you can have a bale of the finest dairy quality hay, but if you got a sore mouth cow, she'll starve to death. If we have acidic soil and problems and we damage the root system, that's the mouth of the plant. So that plant could starve, even though we've got plenty of feed. So one of the things that, and Sandy will talk about soil testing here, one of the things that I recommended, sampling depth becomes really important, and people take a look at this. The thing I suggest is continue your sampling depth, maintain your soil test history so that you can, just like Dave was able to do, go back and take a look at soil history. But every so often, might not be a bad idea to pull a 3-inch just randomly here and there. Let's do a spot check and check surface 3 inches to see if this is developing. Because we can fix this, we can take care of that and correct it. But it's something that can get away from us. Now, another thing that we see happening is soil nitrates. We've had a lot of questions. People say, hey, my nitrates are higher. In fact, over time, we've lost a few customers that said it's impossible. I haven't put any nitrogen on, and you're telling me I've got 50, 100, 150 pounds of nitrogen in the soil, and you guys are wrong. And your lab's screwing up. And we've gone to retest it, but it's a real thing. This happens to be a friend of mine. He was went to college with. He was working on his master's degree in Nebraska. This is up in Alliance, Nebraska. Up, it's where the Panhandle kind of north, where the Panhandle connects to the rest of Nebraska. It's up in that area. 15-inch rainfall, so it's dry. And what this bar chart is showing is year by year by year, the average precipitation in June through August. And so he was going out on fallow wheat plots and looking at soil nitrate. And here's what happened. When we got to 1980, we had that was a severe drought year. Up until 2011, I think that held the record for drought. But in 1980, we had a severe drought. But we had 120 pounds of nitrogen. Now they were sampling the 4 feet, but 120 pounds of nitrogen, and it was a real thing. And we see this happen over again. Now there was no fertilizer. This was fallow wheat, but we do have soil is not styrofoam. It's easy to think about nitrogen as checkbook. You know, we put 200 pounds in, we take 150 pounds out. There should be 50 pounds left over. That doesn't always work. Sometimes we can put 50 pounds in and take off 100 pounds and still have 100 pounds left over. But why is that? This is a diagram that shows the activity of the microorganisms in soil that break down organic matter, break down residue, and convert it to nitrate. So we've got this red line represents the organisms that do the decay and break down the organic matter, a lot of fungi, that sort of thing. The dashed line represents microorganisms that then take that and convert it to nitrate, to plant available nitrate. And the peak activities here, they talk about water-filled pore spaces. So it's the spaces in the soil, the holes in the soil. When about 60% of the pores are filled with water, 40% with air, that's sort of optimal. And that's about field capacity. So after a good slow rain, 2-3 days later, a soil that's not sopping wet, but good moist soil, that would be field capacity. And as that soil dries out, we can get down here to fairly low soil moisture. This could be the moisture we'd see in the drought situation. We've still got 40 and 50% activity of those microorganisms. So even though it's hot and dry, plants may not be growing, but the bugs are still working.
Are you generally talking about CECs at 15?
Just in general, well, yeah, this is sort of general. This is probably looking at heavier textured soil. Sandy soils, I think, trying to remember, it goes more or less, but sandy soils be a little different. The numbers here would be different for sandy soil. The principle is still going to be the same. It's still going to happen. So soil moisture has an impact, but soil temperature has a big impact. This is a lab study where they looked at a soil that had no, just naturally, the microbes, they were measuring nitrate produced. This was in a lab setting. So they maintained a constant temperature here of 60, 70, and 85 degrees and looked over time, over a period of about a month. And cooler soils, microbes are just like us. These bugs are like us. They're not working as hard today because it's cold. They're going to work a lot harder. As that temperature goes up, we're the same way. We can work harder. Now there's an upper limit to that. But in this example, after after almost a month of 60-degree temperatures, at 85 degrees, we had almost 3 times as much nitrate mineralized from the organic matter. So the temperature has a big impact. Now, this scientist took this data, and this is calendar days, converted to degree days, just like we do with corn and milo. Well, we wrap that together. What happens to our crop maturity? What happens to corn and milo in a hot, dry year? We can harvest earlier. We generate growing degree days much faster. The same thing is true with soil microbes. Those microbes are plants, if you will, and they are affected by temperature just like the above ground plants are. So in a year like, I know I did took a look at some soil temperatures. in year 2011, our severe drought, we generated, we were at the end of the season in a lot of areas, we were 30 days ahead on degree days, the soil degree days, because we were their degree days. So the point is, even under drought conditions, those plants, they need to drain, but they can operate under fairly dry conditions. And they work harder and they work longer. And so we can tend to see those nitrates show up. This is an example I used, a good example. Lucas had me put a presentation together here a couple of years ago. But this is the Palmer Drought Index for 10, 11, 12, 13, 14, and 15. And in 2011, this dashed line, that's I-70. It stopped at I-70. I remember driving up 81 to Salina and up, what is it, 183 up to Norton or whatever. 10 miles south of I-70, it was bone dry, things were dying. 10 miles north, you know, in the summertime, it was green and growing. Well, then in 2012, the drought moved up into the Dakotas and over in the Corn Belt, and all the Iowa and Ohio farmers were crying the blues about their drought. Well, in 2013, he still maintained it, but it dropped off. Well, what I did was I went through soil samples in the summer from western Kansas, the Texas Panhandle, and eastern Colorado. And I graphed them out here. And by way of explanation, these box and whisker plots, here's the top, here's the highest and lowest value that I found in that. It's survey data. This box represents the middle half of the data. So there's a fourth below and a fourth above, and that line represents half below and half above. So if we take a look here, south of I-70 in 2010, north of I-70 looks pretty similar. In 2011, all of a sudden we see a whole bunch more nitrate showing. And that corresponds to that drought index. In 2012, the drought moved up. Well, south, we were in their second year of drought. Here, they were in their first year of drought. And so we see those nitrates jump up. Then as we resume normal temperatures, we start getting better plant growth, better uptake, that sort of thing. We see it drop off. By the time it gets to 2015, it's very, very similar. So if you see high nitrates, higher than you expect in that soil sample, it's a real thing. Now, how much faith, you know, how you use it and what you do with it, that Lucas is on deck. We'll discuss that, I believe. I want to spend some time talking about soil organic matter because that's a hot topic. You had the no-till conference and soil health view and some other things. When we run soil organic matter in a lab, this is what we do. We take a small amount of soil, 1 gram. It's about a half a teaspoon or a quarter teaspoon, a very small amount of soil. We weigh it, we cook it, burn it off, and we burn off the organic matter, and then weigh it back. And so what's left is the sand and the silt and the clay, mineral materials. And the difference we report as a percentage of organic matter. So this is what we do for organic matter. We hear the term soil carbon. There's a lot of talk about soil carbon. Well, any material that has carbon in it is organic. So soil organic matter is about 56% carbon. Manure is 8%. We are about 10% carbon. Roundup is 21% carbon. So by scientific definition, Roundup is an organic chemical. It couldn't get that past the organic certification, but it is organic. Cellulose, paper, is a carbon. Diesel fuel is a carbon compound. When I was working this through, my first boss told me once, he said, he gave me a piece of advice. He said, you know, you should never ask to be paid what you're worth, because your boss might just do that. You might not like the answer. So at 10% carbon, I figured out, I work out, if you boiled me down for biodiesel, I think I'm worth about $7.50 as I stand. So worth less than a $10 bill. But yeah. Now, organic matter, when we talk about it, it's not just one thing. There's a lot of different types of organic matter, hundreds of different. There's scientists spend their whole career studying organic matter. We can kind of break it down into these characteristics. Now, when we talk about the plant biomass, we talk about the residue. That's residue. That is not actually organic matter. It's not decayed, it's not entered the system. In fact, people talk about, when we prep the soil sample, we grind it. We have a flail mill grinder, we grind it, we pass it through a 2-mesh or a 10-mesh screen. So when any pieces of leaf or residue, stem, that sort of thing, we don't analyze it. That's gone. So what we're measuring is the actual soil. So we've got root systems, they're living and active. We talk about the microbes in the soil. Now those are living and active. They are actually part of the organic matter. We have dead organic matter, but it's what we call active. There is degradable organic matter. It's dead, it's inactive, and we call passive organic matter. That's very dead and very inactive. So we're talking about, is the organic matter alive? Is it dead? And how, when we talk about how active is it, we're talking about how rapidly it changes from the form it's in into another form. So when we look at each one of these, we accumulate organic matter from the root system, from the residue. The bugs break it down, decompose it. And as they decompose it, they release minerals. This is how my grandpa and great grandpa and whoever else, they didn't use commercial fertilizer. They depended on the soil organic matter to supply them with the nitrogen and phosphorus, especially the nitrogen. As that organic matter gets more and more, we'll say they're more complex compounds, it actually stabilizes and binds together and provides a soil structure. So this type of organic matter here actually gives the soil its dark color and helps with the aggregation. So if we think of organic matter, one way we can think is how long does it exist in that particular form? So maybe days, maybe months, maybe years, maybe even centuries. And as I look at these type of organic matter, think of organic matter, think of molasses, varnish, epoxy, and asphalt, because those are all carbon-containing compounds. I'll show it later. But most of the organic matter is actually down here in this material. We have a few hundred pounds here as microbes and this active organic matter. This is the stuff that we talk about providing nutrients. This is the stuff that we talk about providing structure and stability in the soil. So organic matter, different compounds have different functions. Where organic matter has received a lot of attention is as the microbes break down the organic matter, break down the residue and convert it, and then as they die, their bodies are broken down and we release nutrients back into the soil system. We release carbon dioxide, just like they're doing work. They're just like us. When we do work, we release carbon dioxide, we respire. So when we break down organic matter, we release carbon dioxide and we lose carbon, if you will, but it goes off as carbon dioxide. And that gets into this whole, I'm not going to get into global warming, but that's where the attention comes into play. We talk about carbon sequestration. We're trying to capture and keep the carbon in these forms here, and eventually into these forms here. So that's what we're talking about. Now, organic matter is not just one thing. I ran across these photos by way of explanation. There's different types of organic matter. Like I said, it has different forms. Now these are some microscopic photos. These are pictures of bacteria and fungi and some other things. You see these little lines here, they represent either 0.5 micron or 1 micron. And a micron is 1/25,000th of an inch. Very, very small. Put that in perspective, I didn't bring my props with me. I do a talk about soil texture, and I use basketball. And this morning we had fog. You think about the size of a fog drop, you can just, it's hard to see. Well, those average fog droplet is about 5 microns in diameter. So if you think about that as being a basketball, clay particles, true clay particles, are 2 microns or smaller. And I'm talking about soil texture, so I'm talking about clay, talking about silt, talking about sand, different size soil particles. At that scale, a playing card, like a poker deck, would be the size of a average clay particle. Average silt particle would be about the size of a stack of king-size mattress, about 6 feet tall. A medium-sized sand particle at that scale is about a city block in diameter. So we're talking about extremely small things. So you're looking at, imagine this, a playing card here, so you can see the size of some of these organisms. And this is what's called mineral-associated organic matter. Now we have particulate organic. That's residue that's been broken down and chopped up. And that stuff, although it looks small, at that scale, that's kind of like 2x4s, railroad ties, wall. That's the size. So this is most of our organic matter, and most of it is films. It's films. It's kind of like caramel corn, a candy coating. And I talked about that. There's molasses, there's varnish, there's epoxy, and there's asphalt. So it breaks down at different levels. But the molasses, the candy coating, that's the stuff that supplies our nutrients. That's the stuff the microbes feed on. Microbes die, their bodies decay, and they release nutrients. So that's the organic matter that we call active organic matter. And that's the stuff that is important in soil fertility. And that's what one of the things we're trying to accomplish.
On this carbon, what I tried to read about everything I could find on it. A lot of read, that's I know.
I think, yeah, you hit the nail right on the head. Well, I'm going to go and try to maybe discuss this a little bit more, maybe do that, because that it's one thing. When people talk about carbon, okay, carbon and organic matter, we're talking about the same thing. Okay, it's just that organic matter is about double. If we talk about a pound of organic carbon, we're talking about 2 pounds of organic matter.
And you just use that term active organic matter, which was at the top of that
Right.
list previously, but you associated with something like molasses.
Well, think microbes. You guys, I imagine you all feed cattle. You don't feed cattle. You feed the microbes that are in the rumen, okay? Because you got to have the protein, the energy, and I'll talk about that a little bit more. To feed that fat, that rumen is this big fermentation vat. There's a bunch of microbes in there. And they break your stuff down to amino acids and to sugars and that sort of thing. We kind of do the same thing in the soil. So just like we have digestible protein, indigestible protein, you feed sugar, you feed straw. It's a dietary sort of thing. So this is more like that stuff at the top. That's more like the molasses. That's like feeding molasses that
Which is really gonna be something that
Quick turnover.
microbial life.
provides a lot of energy. Yeah.
So why do I hear about like putting humic in furrow when it's so in it?
Well, the reason for it, and there's some people that market humic acid and stuff. Humic acids do have the capability of sort of chelating, capturing. That's the theory anyway, that it holds nutrients and it's kind of provides sort of a slow release. That's as I understand the theory. That's
So even though they're inactive.
it's not about energy. Yeah, it's not about providing energy the way it's providing mineral. It has to do probably more with mineral nutrition. You know, you use chelated fertilizers, some of those things. It's a type of natural chelate. Okay, and I think that's why they're trying to use that. But you're right, carbon credits, and I've heard somebody describe that. This is a wild, wild west. I mean, there's indigo, you got all these other people out there talking about it. But I wanted to talk about this a little bit because the idea of carbon credits, they want to pay you to build soil organic. And I want to speak with that because we've had a lot of questions about that. Gabe Brown lives up in Bismarck, North Dakota. I think he's always at, read a lot about it or whatever. And I caught one of his quotes here. He said, after the past 20 years, he's seen his soil organic matter increase from 2% to 6%. That's pretty impressive. Well, I wanted to look behind the curtain a little bit. Look behind the curtain a little bit. So I dug down and tried to find some research. How fast can we build organic under condition? This is La Mesa, Texas. Katie Lewis she was looking at continuous cotton. She was using conventional. She was using dry cover crop with no-till. 19-year study, about a 20-inch rainfall zone. And her research, she doubled her impact using a cover crop. And, that's pretty impressive. Well, what I did was I went through, and there's a worksheet that put together, if you want to, you can use feed test results and stuff that do these calculations. And these, I'm not going to go through the math, but what I did was I worked using some of her research information through and calculated using cereal rice silage as a cereal rice silage. And if you walk through it, and I've walked through all the math, what it came up with each year, she had about 4,000 pounds of dry matter, not material, but taking all the moisture out. And on average, she increased the organic matter about 0.02% a year. So if we carry the math out, and 6 years times 19 years, 3/10, we did double the organic matter, but the rest of the story is we started out at 0.3 and we got it up to 0.6. But that's still, and you'll see that's still fairly impressive. Well, I took Gabe Brown's discussion and figured a 6-inch soil sample that we're going to have to increase 0.2% per year. And when I ran through the math, you'd have to stack 70 tons of wet rye silage per acre per year for 20 years to do this. So, I'm wondering, well, is there anything else we can look at? Well, one of the things that we have to be careful of is, where do you live? That's one of the, I'll say, dangers of reading some of the farm magazines, reading some of the blogs. You cannot apply necessarily what goes on in one area directly to our area. If we look at rainfall, well, this is actually open pan evaporation. Okay, this is lake evaporation. So as we go farther and farther north, that evaporation decreases. Well, that just tells us we have a cooler and wetter climate as we go farther and farther north. And it gets more and more difficult, or I should say it gets easier to build soil organic matter as we go farther and farther north. Okay, we have a longer growing season here. So any organic matter we accumulate, the bugs are going to work longer and harder through that growing season. We just have a longer time for them to break down and release the organic matter. I showed it going off as carbon dioxide. That's going to happen. As we go farther and farther north, that growing season is cooler, we get more moisture. We get up into Wisconsin, Maine, and up here, we have peat bogs. Well, peat bogs just is organic matter, just simply has not decayed because it's so cool. We get far enough north, we get up into the tundra, those permafrost soils, whatever, those are 50, 60, 70% organic matter. And it has to do with the amount, they don't grow a lot of vegetation, but what grows really doesn't break down. So keep these numbers in mind. So here we're in this graph here, in this somewhere between 90, looks like 60 to 90 inches of evaporation. This is a little bit busy, but what I did was I went through and I took the average annual rainfall for these different locations and roughed out the evaporation, that open evaporation to rainfall. So down here in the high panhandle over at Tribune, we have over 4 inches of evaporation for every inch of rainfall. Hayes, it's about 3.5. Here we're about 3, 2.5 to 3. And Cape Brown up in Bismarck has 2.5 to 1. So if a farmer from Amarillo here is trying to compare to, now keep in mind the rainfall is about the same right through this line, but that evaporation has a big impact. So one way of thinking about it is an inch of rainfall goes about twice as far in Bismarck, North Dakota as it does in Amarillo, Texas. And that's going to have a huge impact. Topeka is 2 to 1. Charles City, Virginia, and Pago, Georgia, this is where Dave Hewlett and Randy Dowdy live. They're the big corn, 400, 500 bushel corn growers. But they're 1 to 1. They're in an entirely different situation. The stress level is different. But my point here is because of this difference, as you move this direction, building organic matter is going to be easier and easier. So to compare building organic matter from this area to this area is going to be real difficult. Now we do have, and steal you, this is the Tribune data, so I hope you don't mind if I get it. But the Tribune experiment station, so there we were at, what was it, about 4.5 inches to 1. Experiment there, been going on for 60 years. Different nitrogen rates, just conventional tillage, and it was originally dry land. So as we take a look at it, we started out there, that soil had 1.4% organic matter level. So after 60 years, here's what the organic matters look like. And we have 0, 40, and 80 pounds of phosphorus and 0 to 200 pounds of nitrogen. With corn, same rates with sorghum. So after 60 years, we have built organic matter in a couple of different ways. If we go back to that 1.4 on the corn, now this is with conventional tillage, not no-till or anything, just normal operation. We built the organic matter without any nitrogen at all, 3/10. And I attribute that to genetics. As our genetics have improved over time, we get higher grain, we get more residue. So we just got more stuff based on genetics. If we go over here to the 200-pound rate, we're 6/10 higher than we were 60 years ago. So we got our first 3/10 from genetics. Our nitrogen rate gave us another 3/10. So nitrogen can build soil organic matter. When we take a look at the sorghum, I thought this was interesting because the 0 plot, we increased by 0.5%. So I guess I'm assuming that's due to genetics. We're just getting better sorghum yields compared to, way back when. I don't know, but we were up 0.8%. But we increased the organic matter with the sorghum more than we did with the corn at the two different phosphorus rates. That's fairly consistent. So Lucas falls in your court with this. We have to talk about that, but it's a real thing. We have built soil organic matter. We hear about
Really, that neither Alan or I have a good explanation. The other important part of that, Fred, is, yeah, I mean, we've definitely seen genetic deals in time. I think the other important thing to keep in mind is, that's fully aerated. And, we're essentially trading normal water for soil organic.
Well, good point. Yeah, that may or may not be a good trade.
I just want to share that what I've heard the last year or so. Because there was a lot of work done on covers at Garden City, and the fact that never really get behind it. Because it didn't have the moisture for it. But that points out that when you do get it, if you've got something where they can use it and keep growing and convert it back into the, you're better than just not having that kind of crop there and just letting it go through that. And that's kind of that argument. Yeah, I mean, one of the things I'd point out about that tricky data is I think what it shows is the value. You got to raise the crop, you got to raise the biomass. That's the most important, because we're seeing those gains in spite of the fact that is full tillage. That's the only tillage. That's the only tillage on the station is this step. The only reason we haven't changed it is 60-some years old. So the fact that we could build organic matter in spite of the fact that we're doing full tillage shows, first thing, and then back to the fertility thing, you got to raise the pile of stuff first. There's this discussion of too much. There's a deal cycle here about a year ago through some of the popular press. So, well, if you're having trouble building organic matter, maybe it's because you have too much nitrogen. And this clearly shows that optimal P, optimal N means that you raise the biggest pile of stuff, which means you have more stuff to convert to organic. And I think that's, to me, that's a takeaway, because that's happening in spite of the fact that you must.
Yeah, you're doing everything wrong before you do it.
Yeah, it's certainly not how we would recommend people grow irrigated chloride.
Right, but we are increasing.
How much did organic matter change from livestock?
Well, if you're I guess it would depend on how intensively you graze. A lot of the organic matter, one of the things to keep in mind, we pay attention to residue running on the surface. How much of that organic matter is the root system? A huge amount of that. I mean, as we've developed maybe more aggressive root systems, denser root systems, that probably has some impact. So removing the top growth, it may have some effect, but I'm not sure it has a lot. You're also recycling it.
Yeah, I would say recycle too.
So to speak. Yeah.
I would just say to the gentleman's point, came round and almost to a person over there at the soil health conference. Their old joke is, don't your cattle have legs? Why are you harvesting silage and carrying them to the cattle? They got all these stories about their silage, their cover crop was so thick and prosperous, they couldn't find cattle in there when they were stringing their electric fence and stuff. So they turn the cattle out on it and it gets recycled right to the spot. And I've got to think that does happen.
Well, yeah, I think so. You process it, you spend it here, you're sending it through a food processor, just like we, make baby food, we blend it up. You're chopping up chopping it up and doing it. So, I don't know that if you're growing a forage crop, you're just growing more stuff. And so you have more of a chance to build organic. So that would be my impression. Long term, I don't know if there's a lot of ifs, ands, and buts in that one. I'm like, one of the things about being an agronomist is you always have the other hand. And there's that story about, I think it's FDR, in the middle of the Depression, he had a table full of economists. And they were, what do we do this? What do we do that? What do we do? The economists, well, if we do it on this hand, this will happen. If we do it on this hand, on the other hand, this will happen. FDR slapped the table down. He said, would somebody find me a one-handed economist? So there are a lot of things in there, but that's a good question. Yeah.
Rick, if you go back to your slide with the innovation and integration. So, one thing I wanted to,
That one.
So tying this back to your worksheet, I think, the biggest piece in here, correct me if I'm wrong, this would show up in like items I and J in your worksheet. The other big piece of this is oxidation, how much of this we're burning off.
Right.
Before it has a chance to be converted into more stable form. And I think that's a big driver too, is to think about why it's so much harder to build
Right.
at Amarillo than it is Bismarck, North Dakota. Well, you have that heat. In fact, what Fred talked earlier, microbial processes. What temperature do microbes start to shut down? Well, Amarillo is above that temperature a lot more days of the year than what this. So there's that more time where we got oxidation and mineralization. So you look at like those conversion factors under items I and J on the Fred sheet there. Those numbers are going to vary as we move south and north.
It's just like cooking. You leave the roast beef in the oven. The longer the longer you leave it in there, the less roast beef you got. So yeah, that's an important consideration. I'll want to take ahead a little bit here. This term carbon to nitrogen ratio, you read about this thing, and I always struggled with it. I had it in college. We talked about. So what you'll see tables here. Soil organic matter has a carbon to nitrogen ratio about 10 to 1. You got all these different all the way here to sawdust is 400 to 1. Okay, what exactly does that mean? Well, what I did was I broke it down and I looked at what does that mean in terms of percent nitrogen. Okay, and so a lower ratio means you have a higher percent nitrogen, and a lower percent nitrogen here in sawdust. Let's take it a step further and think about it as a soil microbial ration. And I worked through the numbers, and in essence, this is the protein content of these materials. And like I talked about rumen, you're feeding the microbes in the rumen. Likewise, you're feeding the microbes in the soil. And what we found is at a C/N ratio about 20 to 1, or about 10 to 15 roughly, protein ration, those soil microbes are stable. You don't really gain organic matter, you don't really lose organic matter, it just keeps it in equilibrium. If it's less than that, higher protein diet, we break down and we release nutrients, we release nitrogen. If we have a low protein diet, it's just like cattle, the performance is poor. So we get immobilization. Now, these materials, because we talk about immobilization, we talk at this, it's more slowly decomposed. This is the stuff we build organic matter with. This is not the stuff that we build organic matter with. So our high protein stuff, we don't build organic matter. Our low protein stuff, we do. The residue, the stems, the stalks, that sort of thing.
And that immobilization comes back around to minerals.
Eventually, it can eventually, but it's just a longer time frame. So, that's one of the things about organic matter. You have to think about it in terms of a year, 10 years, 100 years, and the time frame has an awful lot to do with it. This was this was a study that's done in Iowa, 4 locations in Iowa. They looked at corn or corn soybean rotation, different nitrogen rates. Now, this is all non-irrigated, but in Iowa here, we're talking 30, 40-inch rainfalls on it. And this is what they found. What they did was when they looked through all the data, the change in soil organic carbon as we increase the nitrogen rate, and this is a percentage because these are different nitrogen rates and what have you. As we increase the nitrogen rate and got to what we call the optimum rate, we built organic matter. Now we had a slight level out or a slight decrease, but with the corn soy rotation, we didn't generate organic matter. That's because, first off, the soybean residue in that rotation, we just had less stuff out there. We had more stuff when we had continuous corn, but the soybean residue is also easier to break down. It has a higher, I should say, a lower carbon to nitrogen, this higher protein product. And so it broke down, the microbes broke it down, and it was released. So we didn't really build soil again. But in their research study, this was kind of a good component. They had what they called the agronomic optimum nitrogen. And that's where we add nitrogen up to a point where we hit this plateau. So we increase up to this point, and no matter how much more nitrogen you put on, you really don't increase yield. You reach a peak point. That may be 180 pounds, that may be 100 pounds or 200, whatever. The change in yield, that first pound of nitrogen we put on, as more and more nitrogen we put on, the less and less yield per pound of nitrogen increases until we reach a point where it makes really no difference. And our carryover nitrogen increases once we get past this optimum level. And so we increase the carrot nitrate, we get to excessive nitrate. And one of the things that they did found that you can, under some situations, you can decrease. And Lucas talked about that. The myth is that we use nitrogen, we burn up organic matter. Well, no, we don't. We build organic matter with nitrogen. But if we have excessive nitrogen, past what we need for decent yields, excessive nitrogen, you can stimulate those microbes. That's what that soybean residue is doing. And so you don't really build organic matter. So managing nitrogen correctly becomes really important in managing the organic matter. And I thought this was interesting. This is a summary of all their stuff, but take a look. What they did was in the continuous corn, they generated about 100 pounds of organic carbon, 170 pounds of organic matter every year. And do the math on a 6-inch sample, that is about 1/100 of 1% organic matter per year. And this was a 19-year study, I think, 15-year study. But then when I compared it to La Mesa, Texas, 2/10. I thought this was pretty interesting because we're going from Iowa to West Texas, and yet the building the organic matter, even Tribune building the organic matter was not that much different. And I bring this up just because I think that some of these things are, we need to be realistic about what we can do with soil organic matter. If you're expecting to double and get these huge increases in organic matter, It's probably not gonna happen. Now, I will say this, if you're looking at just what's happening in the top inch, you can build that probably pretty fast. You can probably make that change. But that's not gonna have a real big impact on your crop production. We need to build organic matter. Tried to figure this on at least a 6-inch, if not deeper. And that's a much, much tougher thing to do. So I think these slow, gradual increases in organic matter, we can't be looking at increasing our organic matter just in 2 or 3 years. You need to be looking at some of your kids, maybe some of your grandkids, to be able to see something that's really truly measurable in the soil. One of the things I found interesting, this is Andrew McGuire is from Washington State, and there's lab tests that can claim to measure soil health. We've looked at them, but we've kind of classified them under the, they're interesting, but they don't really provide us with information to make management changes. And Andrew came up with this ladder that I thought was a really simple, straightforward way to compare and look at what we call soil health. Does the soil blower flow away? Get good soak? Does it drain? Does it crust or seal off? Can you pick up the nutrients? Do you have a lot of carryover? Do you have areas where plants die? Answering these questions, yes or no, start to give you some information and start to focus in on, okay, here's my problem. Here's maybe what I could do with it. In some cases, their lab tests can help. In some cases, it's going to be a management change. But I think, like I said, I think this is just a really practical way of looking at it and evaluating soil health. This is a way of looking at microbial activity in the soil. If you think back, I talked about cellulose being a carbon-containing compound. Cotton fiber is primarily cellulose. So what they were doing here was they were taking their a pair of tidy whities and burying them in the soil for a period of time, then dig them up. The more microbial activity you have, the more you're going to break down the organic matter. So, the more decay you're going to have. So that's what they were doing here. But had a meeting I showed this at. Somebody offered this suggestion to me. He said, actually, these are from farmers, and they just got done talking to their loan officer about renewing their operating bill for next year. And so that's what things look like. So with that, the end, just to summarize, take a look at our pH. Your pH may drop a bit compared to history. That may be, we hope for the bounce back, but we hope for the bounce back, but yet keep in mind, you want to monitor, make sure that it's not an ongoing problem. We're going to have higher nitrates this year, so we need to evaluate soil nitrates. When we take a look at soil organic matter, soil carbon, slow and steady is the name of the game. We can increase using good net management, good nitrogen management, good tillage management, but those changes can be rather slow and steady, but it can happen. So with that, I'll shut her down.